That was our first step. Now we get a lot of these volumes. So we basically go into our three-dimensional data that we got from the tomograms. We found, so we have the three-dimensional data. We go and look for all the areas with the virus, and we segment out those spikes or envelopes. Sometimes that's done by hand. Basically, somebody goes and places a box around each one of them. Sometimes you can do that automatically. If you have a model of what more or less you expect, then you travel around your image with that model and you do a distance at every place. And if the distance is small, you say, oh, it looks like there is one of these envelopes here. It's very similar to what we did with non-local means. In non-local means, we were looking for similar patches. Now the patch is a model that you have, and with it, you go around. So either one of those ways, either manual or with this semi-automatic, you get these volumes. These volumes can be like 100 by 100 by 100 pixels, representing basically the envelope inside this spike that we have. Now, remember, these are noisy. They're not all the same. We need to group them. We need to align them. And that's what we are going to basically do. We are going to align them first. And they're still very noisy. So the alignment is not going to be great because you're trying to align things that are very, very noisy. But it's a good step. You can actually only, if you want, align those that are basically put a very, very high threshold and very high level of confidence in the alignment. You say, I'm going to align them only those that basically after I align, the distance is almost zero. They're almost identical. So then I have more confidence that I have done good alignment. Once again, alignment is you start and just rotate them until the distance that we show in the previous slides becomes the smallest possible. Once you have them aligned, then classification becomes a bit easier. So you say, okay, now I have them all aligned. I have them all in a common space. Now I want to group them to try to only put in the same group those envelopes that basically have the same three-dimensional shape. And there are many ways of doing this classification or clustering that we need there. But let me just illustrate to you one example. So you have all of them aligned, and now you have the distance that basically led you to the smallest alignment rotation. So you align them, you rotate them, you align them, you have the distance. And now you basically, how do you group them? You group all of them. So you pick one and you say, hey, bring me all my friends. Who are my friends? Don't have very small distance to me. That's one group. Then you pick another one and say, bring me all my friends. And who are your friends? Those that I got very small distance. So you basically group them. Once you group, if you did everything right, you can basically average them. And we know that the average will reduce the noise. That's what we talked before. We explained when we were doing image denoising. So you can kind of denoise them a tiny bit. And after you denoise them a tiny bit, you can say, hey, let's try to align them again. Now they're a bit more clean images. So we're going to align them again. We're going to cluster them again. We're going to align them again. And we're going to cluster them again. And you repeat that for a number of iterations until you're satisfied either that things are not changing too much, or basically you say, this is the best I can do, so I'm going to stick with that. And that's a process. We define a distance, we do alignment, clustering, alignment, clustering. And the big thing here, once again, and we're going to come again and again to that, is we have a lot of these small boxes. Now, I want to reiterate to you, all this is done in 3 dimensions. These 100 by 100 by 100 cubes, we have like 4,000 of them. Sometimes we have 10, 20,000 of them. So a lot of computations. We need to align everybody with everybody. We need to compare everybody to everybody. We need to do that many, many times. You can speed up this using different, basically, tricks. One is for this particular case, going to Fourier domain. Normally, these things are implemented in GPUs and very, very efficient implementations to make them run in hours and not in weeks. So that's what we have. The most challenging part computationally is this alignment part, because we have to basically try all these angles, and that's normally done in the Fourier domain for this type of examples, as we say, because of the missing wedge and because of the speed. Now, you have an algorithm. You develop this image processing algorithm, and you're going to use it to detect the three-dimensional shape of the envelope in the HIV virus. But then you say to yourself, how do I know if my algorithm works? Nobody has ever seen the envelope at the resolution that I want to see it. So how can I validate? And this is very important when you're talking about medical imaging, because you don't want to make mistake and mislead, let's say, a complete vaccine development because you made a computational mistake. So what you do in most image processing, but in particular when you're talking with medical imaging, is you go slow. First, you start from what are called phantoms. You create three-dimensional shapes that look like viruses from your prior knowledge. You add noise, you project them, you make missing wedges, so you make them like they were acquired in the microscope. And you run your algorithm for that. You know the ground truth because you created it. You hope to reconstruct. Until you don't finish that, you don't move on. So you solve this. You say, great, I put different structures, phantoms I created, I rotate, add noise, add missing wedge, I got them back. I'm happy. The next step, because it's almost impossible to do a perfect simulation of everything that is going in the microscope, is you take particles that for some reason we know their structure. Maybe because they are larger than the HIVs, maybe because they are more rigid and they could be acquired with other technologies. And one of them is what's called the GROEL, G-R-O-E-L. So you go into your microscope, you put GROEL, you run your algorithm, you get the 3D shape that everybody knows is the right shape. You say, okay, this is as much validation as I can do. Now I'm ready to do HIV. Even here, you can do a lot of validation. For example, you can take these 4,000 samples and drop 500 of them, do your computations, then drop a different 500 at random, do your computations, and you expect to get very similar results. So still here, you have to do a lot of validation. But this is a regular progress. Phantoms, no data, and then you go into the unknown, which is the HIV. Remember, we're looking for these tiny spikes here, and we're talking about basically Armstrongs. That's what basically the sizes that we are talking. Now, let me reiterate to you why this is so important in this schematic. These are what we have been seeing. Let me show that again. This is basically a true example from this cryotomography, one slice. And now this is a schematic of that. Now, as I say, when it goes and tries to latch itself into the membrane, it actually tries to basically grab from something which is called a CD4 here. And then the virus has these two components that are the GP120, basically this red, and the GP41, this blue. And it's like, you could think maybe as a flower that is opening and then trying to latch into the CD4. And once again, it's very important to understand how this conformation is latching, how it's contacting, how it's basically managing to grab the CD4, and are there any changes happening when that's going on. Now, this has been very, very elusive. It's very, very hard to find, but this is the importance. Again, we have the schematic. This latching, this contact is critical for the virus to go into the host cell. So that's a very important step here. And I was lucky to work on this with people at NIH, at the National Institutes of Health, and I'm going to show you some results of this, and much more research has been done on this area, but this is important and enough to illustrate the example for this image processing class. And normally what you do is you basically have the virus in different states, and then you try to look at this 3D shape in different states. And for the particular examples I'm going to show to you, we have 400 viruses. From them we got 4,000 of these spikes and envelopes under different states. So what's called unligand with a B12 complex and with other complexes. So just different states. We want to concentrate on the image processing part. This is what you see. This is your raw data. You put the virus, you did the cryotomography, you basically put all the tilts together. This is what you see. And you say, oh boy, what am I going to do with that? But you remember that you just developed an algorithm that is working for other things. So you plug your algorithm into that. You find the envelopes, you do the alignment, classification, alignment, classification, and then you start seeing progress. You start from basically, this is kind of the very beginning, nothing looks okay. If you align things which are completely if you average things which are completely non-aligned, you just get balls. It's just everything going in every direction. Then things start getting better. Things start to appear, and you start seeing shapes. You didn't see anything, and after iterations you start seeing shapes because you are progressively improving your alignment, improving your classification, and then we know that if we average things that are the same, the noise goes down, and then we can get the shapes that we wanted. So we go from this, which kind of has it there, so we can see them here, and that's where you go and you either automatically or manually, as we say, you pick all these particles, and then you can get your reconstruction. This is actually obtained from the tomography, and what we really want, so we are starting to see the 3D. This is just one of these. It doesn't have to be exactly this one, but it's one of them. You see that, and you see the envelopes. And basically, you average and classify those envelopes, and here's what you see. You have the membrane that you were expecting, and I'm going to just run this video. And this is the shape. This is the envelope that you were looking for. And then you try to fit pieces that for other reasons are known, and you see, oh, this is one of my validations. Nobody has seen this in its entire composition, but they have seen pieces of them. So let's just try to bring them and see if we can basically fit them properly. So this is the envelopes that you see here. How you go from here to here? Smart image processing. Once you have done that, you can start doing the biology. And this is what the people from biology teach us. That is the important part. Why are we doing this? They come and explain. Because now I can look at the HIV envelope under different states and basically see that their shapes are different under different states. And then you can start making biological conclusions about that and say, under certain conformation, this is what happened under different state when it's actually latching into the CD4, it's changing shape. And that's extremely important for the vaccine development people. And then the interaction starts, and then they ask you more image processing questions, and then you try to address that. And that's what we basically illustrate here with a schematic, that basically there is a change in shape, a change in conformation when there is CD4 binding. And that's what we illustrate here with this change in the arms, kind of an opening. And you can see this with image processing. You couldn't see that with your naked eye. This is one of the really exciting areas where image processing actually helps you see something you couldn't see before. When we talk, for example, about activity classification, that was to do in the computer something that the human knows how to do. Here is to do something that the human cannot do. We cannot see the 3D shape just from those projections or from those tomography 3D reconstructions. We need to do this image processing. I hope you had fun. This is an exciting area, and this is just the tip of the iceberg of research in image processing and viruses and microscopy. But it's an illustrative example about the power of image processing to solve real problems. We're going to see more in the next video. Looking forward to seeing you then. Thank you.